Yeah. Okay, now we'll get started. So I posted some labs, and it's kind of this series, lab 5, 6, and 7. Labs aren't supposed to be a thing that takes a tremendous amount of time, so this one will take enough time to be 3 labs, I think. It might take less time than that, we'll see. It says there's instructions on this lab on how to get it to work on the computers in this room. And basically you have to get this file and this make file and make them and fix any problems and insert the module into the kernel. And so you might have to install a Linux source, and depending on which machine you sit down on, there might be other things too, or there might not. It just depends on which one. Most of that bank over there has been used for this stuff a year ago. And so for the most part, they have the right packages. So I suspect a lot of this isn't going to be that big a deal. Okay, now if you want to do this not in the lab, and I can think of at least one of you who's probably going to use this solution. The computers in here, this is what they're running. It's Linux 3.13.0, and this is the standard one for whichever Ubuntu version this is. And this appears to be trusty, so I guess you can count on it. So I don't know which version Ubuntu trusty is off the top of my head.
12 something.
Yeah, 12 something. And Wikipedia actually has a better list of these things than the Ubuntu project, in my opinion, because if you scroll down to this release timeline right here, you can see all of them in a font that you can definitely not read from back where you're sitting. And it actually looks like we're a little later. Trusty here is 14.04. And this is now, this blue line right here. And so actually the previous LTS release, Precise, is also supported at the moment. And it actually will be for another year and a half. But anyway, these appear to be running 14.04, I guess, seeing it said trusty there on the package repository. I kind of felt like they were older than that, but evidence is against me on that one. So, there you go. That's the version. So if you wanted to install this on your own machine, you just go to the Ubuntu website here and download, and it'll have some options here. I think it'll probably, oh, look at that, 14.04, the long-term support. That's what we were after. And you can download it right here and install it on a virtual machine or actual computer or whatever you like. I've never really liked virtual machines for some reason. They just feel really fake to me, you know? It's like, I don't know what it's like. Anyway, it's not running under real hardware. They're actually a great tool for developing kernel modules because you can turn them on and off again quite easily, and you can host it on a computer that actually stays up and keeps working, and yeah, there's many reasons that they're excellent. And I don't have any justification for disliking them, and you're absolutely welcome to use one, but I don't like them. So, I'm not going to use one. Okay, so anyway, you can set up Ubuntu for yourself or not, and you'll need Linux source for sure, because Linux source actually has stuff that this will get built against, and then from there it should pretty well just work with these instructions, hopefully. Okay, there's a Linux kernel development manual, and it has an explanation of this program here and how it works, and so you can go through it and learn about it in more detail. The other thing is, this Linux kernel development manual is actually written for kernel 2.6, and that's not what we're using anymore. And so I adapted it for kernel 3.2. I did this last year because I was running kernel 3.2 on my office computer, and 3.2 is mostly compatible with the 3.13 up here. I did have one example that didn't work when transferred, but for the most part they did. And if you look at the information on here, we're on 3.13 here. Isoptera, where you don't get to test kernel modules, is actually running a little bit newer one. It's running 3.16. Anyway, they're mostly compatible, but it's this mostly thing that sometimes gets you. And I know this worked just fine last year on 3.13 in here, so if you want an easy path to success, I might suggest that. Anyway, but it did work fine on 3.2 as well. Okay, so that's that. And then for lab 6, you get to add a file in /proc, which you're going to use to control it. And it's set up so when you read from the file, it starts or stops blinking. And say you just read to start it, and read to stop it, and if you read again, it starts and stops. You know, it just flips back and forth. And so the initial state can be either way, it doesn't matter. And then finally for lab 7, you got to set it up so the user can actually write something and control this blinking and actually deliver some information here. So I'm assuming that these things will average about 2 hours, so I'm thinking this is probably about 6 hours of work. That's my guesstimate. It's kernel development stuff. One never quite knows. Have you ever seen an upgrade comic? Probably. Kernel development is like this. So, you know, you start out with good expectations and they kind of go down as you go. And, you know, eventually you just end up at the end state of the project. Part of the reason that this kind of thing happens is with the kinds of projects like that, you know, he's trying to do a BSD that involves waiting for computers. If you waited for a computer because you're working on it, sometimes you start taking apart a different computer. This happens to me. Like I was building a computer in my office the other day, sitting on my desk, taking up most of the desk, the area where people actually sit. You know, it's behind a big computer now. And so it uses this Intel Turbo Boost technology. And with Turbo Boost, basically what Intel, the processor in there will normally run at 4.4 gigahertz, but has this Turbo Boost to 4.4, which is 10% faster. And it will only run at 4.4 if it's got one core fully loaded and the other 3 are lightly loaded. And I've always assumed this is due to thermal dissipation. The other candidate here for why you could run one core faster but not the others would be power consumption. But it's in a motherboard that delivers plenty of power. And in some applications, it might be installed in a motherboard that has weak power delivery circuitry. Incidentally, when you buy a motherboard, just buy the best motherboard. You'll be happy. Anyway, so the thermal dissipation. So I put a bigger heatsink on it. It's about 4 times the volume of the one that comes with the processor. And it'll just kind of run at 4.4 straight up all the time, even with all 4 cores fully loaded. I haven't stress tested it that way, but I was like, oh, I should do the same thing for my office computer. So I got that set, and so now it runs at 3.9. It's a little older. It's 3.9 is the turbo frequency, and I did stress test that, and it checked out good. It didn't even get hot, really, with the heatsink that's on there. And where am I going from this? I'm sorry. I just started a massive tangent for no reason. Oh, anyway, so
that's how the computer works, though. You always get on tangents while working on one.
Yeah. Okay, so I was going to talk about curve modules. This is going to happen. I slept like 2 hours last night total. My head was feeling like it was going to explode, and it made it hard to sleep. I don't know why. Okay. I had some notes for today, too. I should go find those, because otherwise I'm not going to say anything of value all day.
So is there like a hardware trick to make it keep turbo boosting? Or?
Yeah, I just go tinker around in the BIOS for a while.
Oh, it's in the BIOS?
Yeah, I actually use the overclocking settings.
Oh, okay.
And I actually turned mine up to 4.1, my desktop, and it acted fine, but I didn't leave it there because I wanted no trouble with it.
Then I probably can't do that, because I was going to say I have turbo boosting, but it never works.
On that?
So, yeah.
That's an Apple.
Yeah, no.
Yeah.
It's like they advertise turbo boosting, but it never turbo boosts.
Oh, that's too bad.
It'd be nice if it did. It's at 4.1 in a laptop. I mean, that's
nice and fast.
Yeah.
Yeah.
I don't recall how fast my computer's CPU is. All I know is that my motherboard auto overclocks, so I'm all good.
Yeah, I run my home one. It's stock 2.4. It's a little older. Run at 3.0 on the stock heatsink, no less. 24/7 works good. If you pick a CPU well for overclocking, like you pick the bottom end of the model range on a batch that's known to have good yield, you can usually get at least to the top model in the range. And so it saves you a couple $100 over just buying a top model. You can have stability problems. If you really want to get it overclocked all the way, the motherboards a lot of times will like try to figure it out for you. And so you probably just let it try to figure it out and start there if it has that feature. If not, it's fine. You can do the traditional way. Traditional way is you just overclock it by like 5% and boot it up and do a stress test. And if it's still running after an hour, then you shut her down and go for 10%. And so on. And eventually you figure out where you can get to. And you just back off. I don't know, back off to the previous spot. And yeah, so a lot of times when you do this though, when we're in these kernel modules, you can see how if the kernel goofs something up, that can cause problems. Like last time we blew up the webcam. And so if you're going to be stress testing your CPU expecting to eventually hit a failure point, you probably want like a read-only file system, like boot up off a CD or something, or a USB drive that you can format right away or whatever, throwaway partition. Okay, so we made proc directory entries, and so we got a module into the kernel last time, and I make a cryptography services module, and so Linux has cryptography services in it. There's a number of algorithms. If you took the security class, these will be familiar. You got AES, you got RC4, you got RSA, Blowfish, a few others integrated into the kernel. And having the services integrated into the kernel gives a consistent implementation. And the idea is that way, when a program needs to do some cryptography, it accesses cryptography services, and the kernel does it, and everything is great. And it's better than having everybody write their own buggy implementation. There's a key exchange algorithm, Diffie-Hellman key exchange, which actually wasn't covered that well in 430 or 475. Anyway, Diffie-Hellman, basically it's a way to exchange keys without being physically present. But it depends on agreeing on a couple of numbers. And in principle, it doesn't really matter what the numbers are. They just have to be factors of the same prime number, kind of the same as the RSA problem. And there's a potential attack on this, assuming you know those numbers, but it's highly computationally intensive. Well, there was a program out there, a popular program, I forget which one, where the writers of the software just embedded a couple of primes in the program, like hard-coded them in. And so the NSA went ahead and did their computationally intensive procedure. And so at that point, they can actually crack encryption and figure out keys that were generated by that program. Nobody else's program, and of course, if you change the program to use different numbers, then you would thwart their efforts, and you'd have to go redo their giant computation project in order to crack your encryption, and probably not something that's practical. Anyway, obviously the writers of the program should have done something instead of hard coding the numbers. They should have had it generated differently or something like that, but it's not what they did. Generate a different one for every day of the year. They can't do the process in a day, so it'll be fine. Oh, so anyway, cryptography services in the kernel. It gives you a known good implementation of stuff, and allows things to be computed in kernel space, so that's useful. Okay, so I'll go ahead and make a cryptography services module here. Okay. Okay. So we did some kind of simple test.c one last time, and we had a make file. Okay, so I'm going to change this to compile our cryptography services module. Okay. Okay. So we got this module here, and it's got a write. Well, what we want to do here is allow the user to write something to our file. This isn't how the rest of the cryptography services work. This is just how ours will work. Write something to the file, and then we want to be able to read back the encrypted version. And so all you have to do then, if you're a user of this system, you just write something into the file and then pull out your encrypted version when you like. Should be pretty straightforward here. Okay, so I got this whole write thing, and this is what blew things up and stopped the camera running last time. And the reason was we're returning a 0 here, and so this write function, basically the user from user space is calling write on this file, and that triggers a system call, and inside the system call we're told that the user wants to write, such and such amount of data, and when we return a 0, we're saying that they wanted to write that much data, and we accepted 0 bytes. And so write will helpfully recall this function in order to write the remaining data, as in all of it. So let's do an experiment here, just kind of confirm the way we think things ought to work. We'll put a 1 there. We've got this print k, and I'll do a bit of a call account here. Okay. And I'll put the count right in here. U is for unsigned there. And that actually goes first. Okay, call account plus plus. This will start out on call 0. It'll do a post increment. Okay. So in a moment we'll have built our cryptography services module, hopefully. There we go. Takes a moment. Oh. What do we call our file? I forgot. We should probably name it something else anyway. Our proc file is called simple test. We'll call it crypto services. There we go. Name match. Rebuild that. Make should run faster the second time. The first time, well, make doesn't redo work, but it doesn't have to.
And you didn't rename the removal at the very end of the...
Oh, really? You're right. I would have duplicated a string. Should be like a constant at the top of the file or something. Okay. Okay, so we're in the kernel. It's there. Let's echo hi into proc crypt host services. Permission denied. Okay. So you can see a lot of text. We had this problem last time too, but we didn't blow up the computer and stop the webcam this time. So you can see this is call number 2 there. Let's go ahead and fix some of all this /x, whatever, df.
I have a question.
Yeah.
The pattern that seems to form, is that just random that it's that way, or is it actually...
Well, it's not random. It's based on the line length of the screen. Because I see this pattern, it doesn't evenly cut it off at the end of the screen here. And so it does a little bit of a shift each time. Okay, if we had a different width terminal, we'd see a different angle in the lines there.
Okay.
Including straight up if we had just the right length. Okay, so write was called. And user thinks they're going to write %s to a file, call count plus plus, and buff. So where was that thing appearing? Write was called. too. User thinks they're going to write, and now we see all of this stuff. So I would say we did something wrong with that buffer, probably. So my guess is that percent sign S is expanding into that whole thing. And so if we just temporarily take it out, we should hopefully see that goes away. Okay. Input output here. Uh-oh. Got a some kind of problem in here. Insmod tainted something. Modules linked in. Oh, did I forget to RM mod it? It looks like maybe it got into kernel twice. Okay, let's insmod it. Okay, I didn't see our word in the kernel there anywhere. There's word in the kernel. And now we got some kind of proc crypto services already registered. And something's going wrong here. Okay, we have crypto services in. If we remove it, okay. It's not there. Kill. Okay, this is a little odd. This terminal's sort of stuck. I think the camera still works. I just had to make another terminal button and I didn't see anything. No, I don't seem to be able to make new terminals now. No, definitely can't make any more terminals. And that user interface there seems frozen, except that I can switch frames. And so, obviously the computer is still responding to some extent. I don't know why it can't start new programs.
Cryptography anymore, can it?
Well, that's our crypto services. Like, there's not actually a module called crypto services. They're called other stuff, like AES or whatever. So we didn't run into I don't think we ran into a problem there. I'm a little surprised that it seems unable to carry out new commands. Oh, and the counter has stopped working on the video. So I would say the system is actually pretty done at the moment. Did we actually Yeah, I'd say it's done for. Yeah, it's not going to be growing things. Okay, well, I think we're going to have to turn it off and then on again.